We're going to finish up this chapter on applications of the derivative by doing some applied maximum and minimum problems. Most textbooks would call this optimization. What's going to happen, these problems, they're all word problems like most of what we do in this chapter. And with these problems, what they're going to do is describe a scenario. Maybe it's one where we have decisions that could be made, but some things could be changed. And then they're going to ask us to either maximize or minimize some quantity, all right? So in this procedure, whatever that quantity is, I'm just calling it Q. Sometimes it's helpful to draw a picture. If so, do it. Sometimes that can, give us some insight. What we want to do is then take whatever that quantity is and write it in terms of another variable, another single variable. We often will start out having to write the expression in terms of maybe 2 or more variables, but they'll give us information so that we can really narrow it down to just writing it in terms of one variable. Then we find Q prime. Now this is, we're going to differentiate with respect to whatever this other variable is. So in a lot of what we've done in at least a couple of sections of this chapter, we've always been differentiating with respect to time. We did that in the curvilinear motion section. We did that in the related rates section. Here, we are differentiating with respect to this variable that we use to write the function Q. Now, if we're looking for a maximum or a minimum, we already know from all of this work we've done so far, we did it a lot with this curve sketching the last couple sections, that if I'm looking for a maximum or minimum, that'll happen when the derivative is 0. So we look for potential candidates by setting the derivative equal to 0 and solving. And then we have to check to see, is that a maximum or a minimum? Could be neither also, right? We know that. When you check to see if that solution is a maximum or a minimum, you could make a sign chart for Q prime, or you can check the concavity by finding Q double prime. And then make sure that you answer the question that was asked. Sometimes they ask, what is the value of the variable that will give a maximum or minimum? Sometimes they ask, what is the actual maximum or minimum value of that quantity? So sometimes there could be an extra step where you just evaluate your function. Let's do some examples. In our first one here, a farmer plans to fence a rectangular pasture adjacent to the river. So she's using the river as one of the boundaries. And then for the remaining 3 sides, she has a total of 600 meters of fencing. We want to find the maximum possible area. So it's rectangular, which means 2 of the sides will be the same length. We're labeling those Y in the figure here. And then this other side is labeled X. So there's a couple of things, right? We want to maximize the area of this rectangle. Well, that's pretty easy to write out at first, right? I like to state what I'm doing, maximize or minimize. In this case, we are maximizing. And then what that quantity is that we're maximizing. It's an area of a rectangle, so that's A equals, in this case, X times Y is our length times width. So there we have an equation for the area. You'll notice, though, we've written it in terms of 2 variables, not 1. So somewhere in here, they've given us information so that we can eliminate a variable. So that extra information that is crucial here is that she has a total of 600 meters of fencing. This is clearly pretty crucial information because if there was no limitation to the amount of fencing she had, she could make this as big as she wanted, right? Like there would be no issue about finding a big region. In fact, there'd be no maximum, right? You could just keep going, right? Make it as big as you want. But she's limited to 600 meters of fencing. So we know if the perimeter well, actually, I don't know if I should call it perimeter because we're only including 3 sides, but let me adjust that a little bit. Total length of fence. total fencing is 600 meters. And so that means that I can make an equation relating x and y together. So that would be x plus 2y, or x plus 2y equals 600. Now I could just use this equation to get an expression that I could substitute into the area function. So it seems pretty simple to just solve this for x, I guess. So x would be 600 minus 2y. Now I'm going to take this and I'm going to substitute it into that equation. So now when we do that, 600 minus 2y times y. Now look, we have written this quantity that we're interested in, the area, in terms of a single variable. Now the next step in the procedure says find the derivative. So we are going to find a prime. We're going to differentiate with respect to y. But before I do that, I want to make my work as easy as possible. So I'm actually going to distribute the y. That'll be easier than having to use the product rule. So I'm going to distribute that y. We get 600y minus 2y squared. Now I'll find a prime, taking the derivative. It's a polynomial, so it's not too complicated. 600 minus 4y. And now we're going to set the derivative equal to 0. And when we do that, we get 600 minus 4y equal to 0. Of course, that happens when 4y is equal to 600. And then if we divide both sides by 4, we get 150. So we found only one critical value here, right? There's only one value that makes the derivative 0. We hope it's something that'll give a maximum, but we do need to check still. And so there's a couple ways we could do it. We can make a sign chart for a prime. In this case, I think it's really easiest to just make or to find the second derivative. If I go back up here to this first derivative, 600 minus 4y, just find the second derivative. A double prime is negative 4. It's a constant at negative 4. So look, what this means is that the second derivative is always negative. So that means that A is always concave down. And that means that what we found, if it's always concave down, certainly it's concave down when y is 150. So we have found that y equals 150 gives a max. So this is the value that we're interested in. Let's go ahead and find x. So y is 150 meters. We can find x just by using this equation that we found. X is 600 minus 2 times 150, and that's 300. So we know x and y. Now they didn't ask us for the dimensions, though. They said find the maximum possible area. So we actually want, what we're looking for is a value for a. So now we're just going to find the area. The area is length times width. So that's 300 meters times 150 meters. And we get 45,000. 45,000 square meters. That is the maximum possible area. All right, let's do another one. In example 320, they say, let's find the point on the parabola y equals x squared that is nearest the point 6, 3. So in this figure, we're looking at the graph y equals x squared. They plotted the point 6, 3, and we want to find the point, here it's labeled xy, that is closest. That looks like it could be the closest, right? I mean, if I look at other distances, those all look bigger, right? So it looks like the point on the parabola nearest the point 63 looks like it could be somewhere around there. We want to find out what it is exactly. And if we want to find the point that's nearest, what we want to do is minimize distance. So we're going to minimize, and they've labeled that D in the figure. So we're going to minimize D. We're going to minimize the distance between 6,3 and x. So xy, but we know that this point is on the curve y equals x squared. So in fact, this point xy is really x squared. So this distance, we can just use our distance formula, right? We know how to get the distance between 2 points in the plane. Let's see, the distance formula is x2 minus x1 squared plus y2 minus y1 squared, all under a square root. I'll treat this as my x2, y2, and the 6,3 will be my x1, y1. So this looks like x minus 6 squared plus x squared minus 3 squared. So we want, we know that our strategy is that we want to find, in this case, d prime, and then set it equal to 0. When I think about finding the derivative, we could just jump in and find the derivative at this point. We could say, well, that's, the square root. I'll write that as a 1/2 power. We'd have some stuff to do in the chain rule, and it would work okay. I'm going to try to do this a little bit more simpler. I think it'll be easier to get rid of the square root first. So I'm actually going to square both sides so that d squared is equal to x minus 6 squared plus x squared minus 3 squared. And now I'm going to take the derivative. I'm taking the derivative with respect to x. So when I take the derivative on the left side, we have 2d times, and I'm just going to say times d prime. You could write that as 2d times dd dx if you want. But that's the chain rule at work, right? That implicit differentiation chain rule. On the other side, let's see, I've got parentheses to a power, so this would be 2 times x minus 6 to the first, and then the chain rule would just say times 1, so I'm going to leave that out. And then we have 2 times x squared minus 3 to the first, and the chain rule says multiply by 2x. So here's an expression for 2d d prime. I think what I'll do now is, I guess we have a couple of options, but I'm going to start just by dividing both sides by 2 times d. That way I get the d prime by itself. And I'm going to cancel these 2's. And now I've got a common denominator of d. Up top I have x minus 6 plus 2x cubed minus 6x. So all together, simplifying, d prime is 2x cubed minus 5x minus 6, all divided by d. Now, we have d prime now written in terms of both x and d, and that might be a little bit, seem a little bit bothersome, but it actually isn't a problem at all. We're trying to minimize the distance. And So we know that we're interested in where is d prime equal to 0. So first of all, d is always positive. It's that distance, right? So not only is it always positive, it's never 0, right? So there's no domain problems here. So that d prime will never be dividing by 0, and d is always positive because it's that distance. So I know that when I find the critical values, I can check for the signs, like a sign change, just by checking for a sign change in the numerator. The sign, whether or not d prime is positive or negative, is determined entirely by what's happening in the numerator, the 2x cubed minus 5x minus 6. Now this looks like a generic cubic. There's not really an easy-ish way to solve a cubic like we do with quadratics. So I'm going to use the calculator to help me solve this. So d prime equals 0 implies that 2x cubed minus 5x minus 6 is equal to 0. I want to solve that cubic, and I'm going to do this by graphing this on the calculator. 2x cubed minus 5x minus 6. I guess I'll start by looking at it on the standard window. And okay, so that's actually a pretty good window. It looks like it's right around the value 2. I want to make sure that I'm getting an accurate value, so I'm going to use the tool on the calculator to solve this. So I want to know, this is 0 where it crosses the x-axis. So I'm going to use the function on the calculator. I'm going to hit second trace. That'll bring up the calc menu. And I want the 0. I want to know where it crosses the x-axis, so that's option 2. It's going to ask me for a left bound and a right bound. So I'm just using the arrows. I'm stopping the cursor anywhere to the left. I hit enter. Now it wants a right bound, so anywhere to the right, I hit enter. Now it wants a guess, and you could just hit enter there. And there it looks like it happens at exactly x equals 2. So we know that there is one critical value, and it happens at x equals 2. Now, is this the value that minimizes the distance? So does this give us a minimum or a maximum? And that we can also determine by looking at the graph. Because I know that the derivative, remember the sign, whether or not the derivative is positive or negative, was determined entirely by what's going on in the numerator, and that's because the denominator is always positive. So I know that d prime to the left of 2, d prime is negative, it's below the x-axis, and to the right, it's positive, it's above the x-axis. So we could actually make like a little kind of impromptu sign chart here. We know it's 0 here, we know it's negative, and then positive, and that means that it's decreasing, levels off, and increases. This does in fact give a minimum. So now we're going to find the y-coordinate. And this is the curve is y equals x squared. So our y-coordinate is y equals 4. And that means we can answer the question. The question was, find the point on the parabola that is nearest the point 6,3. So we want both coordinates. So that point that we're looking for is 2, 4. Okay, let's try another one. In example 321, we want to find the dimensions of a 700 kiloliter cylindrical oil tank that has the smallest surface area. So it's an oil tank. Now I'm gonna make what I think is a reasonable and good assumption that this oil tank does not have an open top. It's not just oil sitting out uncovered. So this cylindrical oil tank has a solid bottom and a solid top. If we want the dimensions, that means we want to find the value of the radius of the base and the height. So our goal is to find R and H. And what we want to find the dimensions so that the tank has the smallest surface area. So we want to minimize surface area. So they tell us, oh, the other point here is that 1 kiloliter is 1 cubic meter, so the volume is 700 cubic meters. We want to minimize the surface area, so let's start by just getting the formula for the surface area of a cylinder. We know that the surface area, there's a solid, top and bottom. Those are both circles, so that's 2 pi r squared, right? The top and the bottom are each pi r squared, plus, and then we need the area around, and you might need to look this up, or you might not be a formula you have memorized, but we call that the lateral surface area, the area around the cylinder, and that is 2 pi r h. So we want to minimize that. Now we have the function that we want to minimize. Notice though, this is expressed in terms of 2 variables, r and h. We want to write it with 1 variable. So we need to look for something that we can use to eliminate a variable, and for us in this problem, I think it's going to be the fact that we know what the volume is. We know the volume is 700 cubic meters. And the volume of a cylinder is pi r squared h. So that means that pi r squared h is equal to 700. Now I could either choose to get an expression for r or get an expression for h. I think our work will be easier if we get an expression for h, because first of all, it's just simpler to solve for it. And there's also only one spot that I need to plug it in for in the surface area function. But if I solve for r, I'd probably involve some square roots in there, which might not be as convenient to work with. So I'm going to solve this for h. So h is 700 over pi r squared. I'm going to take that expression and substitute it in for h in the surface area equation. We can do a little simplifying here. So now, let's see, we've got 2 pi r squared plus, oh, and also I guess the pi's will cancel here too. So I got 1400 over r, and I'm going to write that as 1400 r to the minus 1 power, because that's going to be more convenient for taking the derivative. Now this is in a nice power rule friendly form. Let's go ahead and take the derivative. So we get 4 pi r minus 1400 r to the minus 2. We found the derivative. The next step, if we're looking to find a minimum, we want to set the derivative equal to 0. The minimum will happen at a critical value. So if we set a prime equal to 0, then we get 4 pi r, and this time I'm going to go back to writing it in the form of a fraction. 1400 over r squared, that's equal to 0. And now we have an equation to solve. I'm going to throw that fraction on the other side, so 4 pi r is equal to 1400 over r squared, and we can multiply both sides by r squared. So 4 pi r cubed is 1400. Now we can solve for r cubed pretty easily and then take the cube root. So let's go ahead and do that. Let's see, 4 goes into 1400 350 times. So this is 350 over pi. So r is the cube root of 350 over pi. We found just one critical value. So we hope that it's one that actually gives us a minimum. So we have this one critical value. Hopefully it's the one that minimizes the surface area. I'm going to go ahead and just get an approximation here. So I need the cube root of 350 over pi. So I'm going to do that as a 1/3 power. 350 divided by pi, all raised to the 1/3 power. That gives us about 4.81 meters. Now to see if this is a maximum or minimum, I think I'm going to find the second derivative. So let's see. So we have the first derivative up here. A prime is 4 pi r minus 1400, r to the minus 2. So that means that a double prime is 4 pi. That'll be a plus 2800 r to the minus 3. Or 4 pi plus 2800 over r cubed. So we just want to see, is the second derivative positive or negative when I plug in, the critical value, 4.81. So you could certainly plug this into your calculator to verify, but we know that it's going to be positive, all right? 4.81 is positive, and that means that if I plug 2800 over the positive of a cube, that's positive. And then I'm adding it to 4 pi, which is also positive. That has to be a positive result. So that's positive, which means that r, our value of r, the cube root of 350 over pi, gives a minimum. And now that I know that it gives a minimum, I'm going to go ahead and bother with figuring out the other dimension. So we wanted the dimensions, plural, both r and h. So I can use this equation here that we used at the very beginning to help us rewrite the function. And so we're going to have the cube root of 350 over pi, and we're going to square that. And let's evaluate this. Let's approximate this in the calculator. So 700 divided by, and use parentheses here, pi times, and that'll be, if I'm squaring the cube root, that's the 2/3 power. We get about 9.62. So our dimensions are that the height is 9.62 meters approximately, and the radius is 4.81 meters.